Hello and namaste. In continuation with the rectification, the length of a plane curves, we are moving ahead with the polar form, and this particular session is for the part 2. So we'll be dealing with the different type of questions which we have not dealt in the part 1. Find the length of the whole arc of the cardioid. R is equals to A into 1 plus cos of theta, and show that the upper half is bisected by the line theta is equals to pi by 3. So here in this case we have to find out two different things. First of all, this is the length of the whole arc of the cardioid, and the second is we have to show that show that the upper half is bisected by the line theta is equals to pi by 3. Moving ahead, let us understand this is R is equals to A into 1 plus cos of theta. Is you will be getting this type of cardioid which is towards the positive x side, or you can say the maximum side of maximum part of this is towards the positive x axis, right? Now in this case, if you'll observe here, we have got this A into 1 plus cos of theta, and this is the line which is theta is equals to pi by 3. So we have to understand what exactly we need to do it. First of all, let me just make you understand one thing, that is R is equals to A to 1 plus cos of theta. Differentiating R with respect to theta, we will be getting it as minus A sine of theta. So the first one, that is the whole arc of the cardioid, that is the arc BACDO. That is, it is like half part of this particular for the arc of this BAC. So what we are doing it just the upper half of this particular cardioid we are considering. We are just considering the upper half of this cardioid, so which is the part 1, and which is moving from theta equals to 0 till, so this particular theta is moving from this point to this point, that is nothing but it's moving from theta is equals to 0 to pi. In fact, it is moving till this point because of this particular point, and therefore the length of the whole arc of the curve is 2 times the length of BACDO, as I have told you. Therefore, it's nothing but 2 times square root of r square plus dr upon d theta the square. That is just putting the value of r and dr upon d theta, making the square. We'll be getting this type of curve or this type of particular equation. After reducing this further, it's a very simple, just the trigonometry part over here is involved in it. So that means we have to just find out 1 plus x the whole square expansion, and then the part that cos square theta plus sin square theta will come together, and that will give you the 1, and you will remain here with 2 plus 2 times cos of theta d theta. Again, pause over here and try to get whatever we are just getting on the screen. So now again it's 2 plus 2 times cos of theta d theta. Again it's like we are finding out the value of this is nothing but, so we'll be going ahead and getting these values as 4a, because it's again one more 2 will come out of this bracket, because we have written here 1 plus 2 times, so it's 2 times 1 plus cos of theta. 1 plus cos of theta is 2 times cos square theta by 2. So here we have used the formula 1 plus cos of 2 theta is 2 times cos square theta by 2. This is what we have used it, actually not exactly theta by 2, it's a theta because I have taken it a 2 theta. So if it is a theta over here, so it will be coming out cos square theta by 2 as a formula, and that is what we have used here in this case. So it's 4a integration from 0 to pi cos of theta by 2. Again, it's a very simple integration. We'll be reaching towards the length of this cardioid is equals to 8a. Because we have taken it the half, and then we have multiplied here with the twice of that, because of the symmetricity of the cardioid about this x-axis, and therefore the length of this particular entire, now this 8a is the length of the entire cardioid, because we have already considered this is nothing but the 2 times. So we will be getting this as the entire cardioid. The length of this is 8a. That means the length of the upper half of the cardioid is just 4a. Therefore, we will be going ahead with the second part, which we have to take care of. That is, theta is equals to pi by 3 intersects the cardioid at a point A. Suppose for example here it is intersecting at this point A. Now it is intersecting at this point. That means this angle, so suppose we are considering the angle from this point to this, so theta is equals to 0 to theta equals to pi by 3. So 0 to pi by 3. What we have reached to this point. So if you will observe here, we have taken of this particular question from this step. Just let me erase the rest of the part. Yes, so if you'll observe here, so this is because of the part, if you'll observe here, this is 4a, and this 4 is because of the two times we have taken. So this 2 we need not to have it. So you have to just write down 2a here. So 2a cos of theta by 2, integration from 0 to pi by 3. Otherwise you'll have to start it again from this point and again do the same thing. You will be reaching ultimately at the same, that is 2a cos of theta by 2. You will be getting the answer as 2a. That means the upper half of the cardioid is bisected by the line theta equals to pi by 3, because we have got the answer as 2a, but the length of upper half of this cardioid is 4a. So that means what, theta is equals to pi by 2 is intersecting exactly in the two parts of the upper half of this cardioid. That we have proved it over here. Now find the length of the cardioid r equals to a times 1 minus cos of theta lying outside the circle r is equals to a times cos of theta. Now the point of intersection of the cardioid and the circle is obtained as, so suppose for example this is what we are getting it. Now actually in fact I have directly written here how this circle is coming out over here. Otherwise how can you go and reach to this particular circle? Check this out here. So r is equals to a times cos of theta, multiplying this particular entire equation with the r, will be getting it as r square is equals to a r cos of theta. That means r square is nothing but x square plus y square, which is nothing but a into r cos of theta is nothing but x, that is x square minus ax plus something plus y square is equals to or otherwise plus something minus something is equals to 0. That means we need to perfect the square over here. After perfecting the or after finding out the third term, so what would be the third term? A square by 4 would be the third term, that is a square by 4 would be the third term. That means this can be written as x minus a by 2 the square plus y minus 0 the square is equals to a by 2 the square. That means we have got this circle with center at a by 2 comma 0 and the radius with a by 2, and this is what we got it as this particular circle over here. This things we have to understand over here, how to draw this particular circle. Cardioid is again simple, as I have told you, it's 1 minus cos theta, so it would be towards the negative x axis, and therefore we can easily check that intersection. Okay, let me take you to the intersection part also. Again this r is equals to a into cos of theta, r is equals to a cos of theta. Just equating the RHS of both the sides, will be getting 1 is equals to 2 times cos of theta, that is cos of theta is equals to half. This gives us the value of theta is equals to plus or minus pi by 3. That means at this particular point A, the value of the theta is pi by 3. We can easily check that because this is a part in the positive, or you can say the first quadrant, and therefore theta needs to be here pi by 3 rather than minus pi by 3. So you can easily check that this is the another point, or you can say this is the line where theta is equals to minus of pi by 3. But we are looking at this particular point, the first quadrant. Now, okay, just a minute. I'll have to erase this off. Okay, fine. So that means what, r is nothing but, because we have to find out the length of the cardioid, we have to take the differentiation of the cardioid and not the circle. Very important thing to note it down, because we need to have the length of the cardioid, and therefore in the formula of the rectification we will have to take care of the cardioid and not the equation of the circle. Therefore r is equals to a into 1 minus cos of theta. Differentiating r with respect to theta, will be getting a into sine of theta. Taking this up to the, and theta is very strong because we have to have this particular lying outside the circle. That means what exactly we are looking for here? We are looking here for this part which is lying outside this particular circle. So that means this is the entire part we are looking at for. So this is the part which we are looking at for this particular type of question. Therefore, whereas the theta is moving from pi by 3 till pi, and this would be 2 times, because it's a 2 times the length of the arc AB, and therefore we are taking AB length, and this is the part, the lower part is again the same because of the symmetricity. Therefore it's 2 times pi by 3 to pi. Again the same thing what we have done it so far, almost the same what we have done with the cardioid or the previous question. Similar type of steps you are going to get it, and just by solving this simple integration we'll be reaching towards the answer as 4a square root of 3 as this particular answer. The length of the cardioid lying outside the circle. So this is what we have just pause the video, try to go ahead and try to find out how we can just reach from the polar to the Cartesian, and how can we draw the circle with this type of the detailing of from this particular one equation of the curve. And this is about the 4a square root of 3, which is the length of the cardioid which lies outside the circle. This is about the part 2. Stay tuned, stay connected for the upcoming session, upcoming parts on the polar as well as the Cartesian. Thank you. Happy learning.